Hi everyone, I'm Salvatore Tedesco, Senior Researcher at the Tyndall National Institute in Ireland. I'm glad to be here presenting my work at EEE Sensors 2020 on wearable motion sensors and an artificial neural network for the estimation of vertical ground reaction forces in running. I'll first give an introduction on the work, discussing the state of the art and the current challenges. We'll then talk about the hardware and the model developed, and finally the results obtained and the conclusions. Before starting, I will talk a bit about Tyndall, the biggest ICT research center in Ireland, with particular focus on microsystems, micro and nanoelectronics, photonics, etc. In particular, the group I'm working with, the Wireless Sensor Network Group, focuses on developing a range of low power consumption smart sensor systems in a number of application spaces. So, researchers' interest toward the ground reaction forces has been growing steadily due to their association with overuse-related running injuries from the repeated impact loading of the foot. Running-related injuries have indeed a complex and multifactorial etiology, also dependent on aberrant biomechanics and training load errors. Even though their direct measurement of running is feasible via instrumented treadmills, force platform, or optoelectronic system, this is only possible in lab settings. Pressure-based insoles have been proposed as a solution for open field scenarios, but still show several issues in terms of cost and performance degradation over time. IMU-based wearable sensors are an alternative to lab-based assessment, easy to use and low cost. Wearables may provide important insight into the kinetics potentially responsible for injurious tissue loads and support coaches' decision-making in minimizing the risk of running-related injuries. The aim of the present work is therefore to investigate the extrapolation of vertical ground reaction force waveforms for each segmented running stride and the associated metrics using an IMU-based system. For the project, we developed a hardware platform which measures 50 by 90 by 10 millimeters and is equipped with a 32-bit microcontroller, a 9 degrees of freedom inertial sensor, Bluetooth low energy transmitter, a removable micro SD card for data storage, and also a touch button for user interaction. And the obtained sampling rate is 238 Hz and the battery lifetime is over 4 hours. For validation purposes, the load soul system was used to measure vertical ground reaction forces on the plantar surface of the foot. The system has been already validated in literature in a number of papers. Utilizing 3 flexible flat sensors on the front, on the mid, and the rear foot, the system measures the force between the foot and the shoe, regardless of which part of the foot is in contact with the insole. The vertical component of the ground reaction force is computed from the overall pressure distribution. 14 healthy volunteers were recruited for data collection. Participants were asked to run on a treadmill at different speeds, 8, 10, and 12 kilometers per hour for approximately 30 seconds per recording, with both the IMU system developed and the pressure insole for validation. The figure below shows an example of the acceleration and vertical ground reaction forces envelopes in the data collected. Data from the IMU and pressure insoles were synchronized manually in post-processing. Accelerometry data was filtered with a low-pass filter. Angular velocity was used for the automatic segmentation of the recorded trials by detecting the toe off and the heel strikes as shown in the figure below with an approach already available in literature. A threshold of 20 Newton in the vertical component of the ground reaction forces was employed for the identification of the same events with the pressure data. Stances were then scaled to 100 data points from heel strike to toe off, and the ground reaction forces were additionally normalized to body weight. The neural network developed consists of an input layer of 100 neurons, a hidden layer whose neurons adopt tanh as an activation function and dropout as a regularization method, and an output layer with 100 linear neurons. The model was fed with the vertical linear local component of the acceleration signal of each stance and was trained to estimate the vertical ground reaction force component. Root mean square error was used as a loss function to compare the predicted and measured values. A grid search and a leave one subject out cross validation were carried out to set the optimal hyperparameters. The analysis was repeated for 3 different numbers of neurons in the hidden layer, and when using PCA for several principal components. Additionally, 4 vertical ground reaction force matrix extrapolated from the vertical ground reaction force waveform were also investigated. They included the vertical active and impact peaks, the vertical average loading rate, and the vertical impulse. For further information on those metrics, please refer to the reference below. Here I show the predicted and measured body weight normalized vertical ground reaction forces average for all the stances of the test set at a separate running condition at 8, 10, and 12 kilometers per hour. At the top, there are the performance of the neural network only model. It is evident that predictions were highly precise for all the running speeds. Instead, at the bottom, there are the results for the best neural network with PCA model, which was obtained with the grid search and includes 10 hidden layer neurons and 10 principal components. The results are further summarized in these 2 tables. So due to dropout regularization, the different models present similarities at all speeds. So results with and without PCA are largely similar. However, slightly better performance was obtained with PCA at low moderate speeds, with a performance decrease at 12 kilometers per hour. Nevertheless, the neural network plus PCA model with 3 hidden neurons only uses 20.5% of the weights compared to the original model, with limited loss of performance, therefore facilitated the possible implementation on low power devices. Finally, when looking at ground reaction force related metrics, the neural network only model tends to be more accurate on the impact ground reaction force peak, with low errors also on the VALR. However, errors were higher on the active peak and impulse values. The largest error among the metrics was 5.4 on the active peak. Instead, the neural network plus PCA model shows instead higher accuracy on the active rather than the impact peaks, with a larger error in this case of 5.3%. In conclusion, the present study explored the application of neural network and PCA in the estimation of runners' vertical ground reaction force based on the accelerometry collected from 2 wearable IMUs built in-house and attached on the shanks of the runners. Vertical ground reaction force waveforms and loading metrics in running can be estimated accurately and could be potentially moved to low power resource constrained devices with limited impact on the overall performance. These findings may potentially lead to the widespread measurement of biomechanical loads in open field. With this, I would like to conclude my presentation, and I would like to thank the funding bodies who have supported this research. Moreover, I would like to thank you for your attention, and if you have any questions, feel free to ask or contact me at the email below. Thanks very much.